As I said before, a very interesting situation arises if the right-hand side of that governing equation is zero. And that's because the body forces are zero or the rate of change of the body forces are zero. And the exciting part of that is that if the material properties are gone, remember, the material properties were creeping in here through Poisson's ratio, but they're there. If they're gone, then wildly different materials, as long as they're isotropic, will have identical stress distributions for a set of loads. So a piece of steel will behave exactly the same as a piece of plastic. And the implications of this are enormous because this was the basis of the classical photoelasticity methods, where people built plastic models of bridges, of towers, of airplane wings, of all sorts of things, and tested them on small scales and looked at the stresses in the plastic, and then they knew exactly what the stresses would be in the steel, neglecting the body forces. Today, of course, these stress distributions can be captured via finite element method, and we're going to explore this qualitatively using flow nets, which is a kind of a geotechnical term. But for now, let's just focus on phi itself, the area stress function. We will have polynomials for phi. And of course, they have to be at least second degree or higher, because the basis of the area stress function is that if you differentiate it twice with respect to a variable, you get the other variable stress. So it has to have at least a second order to capture this non-zero stress phenomena. So regarding the basic biharmonic equation that we saw earlier, it's del fourth of phi has to be zero, where phi is a function of x and y. Now, I'm going to try to stick to this convention fairly consistently. If I call it phi sub 2, that will be a second order polynomial for phi. So we'll have an x squared, a y squared, and then the cross terms. And then there's constants in front of these. You'll see why it's convenient to have a2 over 2, c2 over 2 acting on y, and then the b2. You could check very quickly, you might want to hit the pause button. Does this satisfy the biharmonic? And remember, there's two formats of the biharmonic. If you can't get your head around this one, use this bubbled format here. The bubbled format is right here. So we could prove to ourselves that this indeed does satisfy the biharmonic. But what kind of stresses are associated with this phi? So let me repeat that. What kind of stresses are associated with this phi? And the answer is that we can find this mathematically. So the x stress is that phi differentiated twice with respect to y. If we do that, we get constant c2. And now I think you could see y divided by 2. If we take that phi and differentiate it twice with respect to x, we'll get a2, a constant. And if we differentiate it once with respect to x and once with respect to y, we get the negative shear stress. And that negative shear stress is negative b2. So clearly what we have here is constant stress. So we have a constant stress in the x direction, a constant stress in the y direction, and yet a third constant stress for shear. And it's constant throughout that body. The next question is, what kind of loading can you imagine would induce such stresses?